Okay, the 1.4 section got cut short and we didn't finish to get even odd functions in there, but I wanted to make a video because it does seem to be a point of confusion for a lot of students. So a function whose graph is symmetric to the y-axis is called an even function. And we're not talking here about what you would consider normal even or odd things. What you've learned of even and odd before, you have to think of it differently, okay? So even in the past you thought, oh, well, it's divisible by 2, odd is not divisible by 2. That's not the case. We're talking about a characteristic of a graph. So it's just one more thing you can add to when you're describing a graph, give a person who maybe is visualizing it a better idea. So even means symmetric to the y-axis, and odd means symmetric to the origin. So honestly, easiest way to remember this, O and odd, O and origin, that's how I remember O symmetric to the origin, odd. And then in terms of is it the y-axis or the x-axis, this graphic right here does a really great job of saying that for you. Here's your y-axis, the one that goes vertically, goes up and down. If I took this parabola, this graph, and folded it in half, hot dog, like long ways over the y-axis, it would match up. Okay, that's what we're saying, symmetric to the y-axis. This one's symmetric to the origin. If I took this piece I just traced, picked it up and twisted it around, it'll fit back on the original graph if I had drawn it a little neater, right? Okay, that's our symmetric to the origin. I can rotate around the origin 180 degrees and still match up. And this is how I remember, is it the x-axis or the y-axis? If it's symmetric to the x-axis, it's not a function, right? If we have something like this, it's not going to pass our vertical line test, which would mean it's not a function anyways. So we're talking about functions, a function whose graph, a function whose graph. So it can't be our x-axis. So the y-axis, my go-to for an even is a parabola, right? A parabola centered on the y-axis, and then odd origin, okay? If a graph is symmetric to the x-axis, like we just saw, it's not even a function. So a function is, in terms of algebraically, right, that was graphically, how can we look at a graph and decide if it's even or odd? But in terms of algebraically, here's how we can do it. If a function is even when for each x in the domain of f of x is equal to f of negative x. Okay, so I'll do an example right there, okay? If I had a parabola like this, at the point 2, it's going to be up here, or just a basic parabola. If I was looking at x squared, which is an even function, this would be 4, right? So at negative 2, it would also be 4. They have the same y values. That's what that's saying. It's just saying the negative version of x and the positive version of x have the same y values. So if a function is odd, then algebraically, for every x in the domain of f, f of negative x is equal to negative f of x. So if you look up here, they show you x, y, x, negative y. So this was f of x, or this is x, and f of x. And then the negative is the one that you have to do the negative x and the negative y to get the right point, the points that match up or correspond, okay? So algebraically, I need to find 3 things if I'm looking at even, odd, right? The first is already given to me. I have to have a function or I'm not going to be able to determine if it's even or odd. So I have g of x here. So I need to find g of negative x, and then I need to find negative g of x. Because if I'm deciding, is this even or odd, I need to ask myself, well, does it fit this? Is it f of x is equal to f of negative x? Or does it fit f of negative x is equal to negative f of x? Or is it neither? It can be neither. It can be even, odd, or neither. So what I also want to do is I want to stay away from choosing specific numbers. If I want a true proof that's valid across the board and no one can say, but what about for blank, right? If you have a proof, the easiest way to disprove it is a non-example, something where it doesn't work. So if you prove it for all of x, then regardless of any number, someone can say, well, what about this number? Does it still work? Use x. So try to stay away from using specific numbers here. So what I'm going to do is I'm going to plug in negative x anywhere that I see an x in the original. So negative x to the third, negative x times the negative x is a positive x, but times my other negative x leaves me with negative x to the third. Negative minus a negative leaves me with, or subtracting a negative leaves me with a positive. So g of negative x, in this case, simplifies to negative 3x. I'm so sorry, negative x to the third plus x. I'm looking at the negative version of g of x here. So I take a negative, I stick it out front, and I just put my whole entire function in the parentheses, and then I just need to distribute this negative. So this ends up being that negative g of x is equal to negative x to the third plus x. Okay, now I need to look at my three pieces I have and compare. So I have three functions here, my original g of negative x and negative g of x. So let me go over again what the differences were. For g of negative x, I plugged in a negative x anywhere I saw an x. For negative g of x, I plugged in the entire function inside a negative with parentheses and then just distributed the negative. Okay. And now I have to say, is it this case? Is it that f of x equals f of negative x? Well, no, because here's g of x, and that's x to the third minus x. And then here's g of negative x, which was negative x to the third plus x. The signs don't match up. So it's not that one. It's not even. So I look to the next option. I could say, I'll write this down here, show my work a little bit. F of x is not equal to f of negative x. So it's not even. So then I say, well, is f of negative x equal to negative f of x? In this case, yes, I have negative x to the third plus x and negative x to the third plus x. They are. They are, in fact, so this function is an odd function. It really just takes some getting used to. You just need to know those three pieces. I will say this, if you don't understand what an even or odd function is graphically and by definition, and you don't have it memorized, these algebraic pieces that f of x equals f of negative x equals negative f of x, you're going to be out of luck when it comes time for proving one algebraically. So either you can draw a graph, you can give an explanation of how your past knowledge of these functions has led you to this conclusion, but if you don't know, if you just wrote even, odd, neither, it won't do anything for you. You have to have proof to back up what you're saying.